Hey class, today we're going to take a look at hypothesis tests for sigma squared using both actually the classical approach and the p-value approach. So let's take a look at that. Before we do that, I want to pick up on two things. First, I want to go back here, and this is something I should have done on page V3. But remember I showed you that the critical values in the p-values pages that had the Excel functions. So I just want to go up here and take a look at each of these, and I'm not going to run through all of them, just the ones that I've done here, so I won't do the homework ones. But let's take a look at this one here, and this would be a chi-square dot inverse dot right tail. And then what you put in here is your 0.05, which is probably your alpha. That's probably what we're dealing with here. And then your degrees of freedom, which are 4. So that's how you do that. So remember, an inverse function is always where you're given a probability, an area, usually an alpha, and you want to find the corresponding chi-square value. Or before we had t inverse functions, or we had norm.s inverse functions. And then remember that the chi-square distribution is not symmetric, so we need to tack on an RT if we're going up, that is to the right. This one here I said I'm not going to do. I'm actually going to lie on that one and say that for this one it's going to be a chi-square dot inverse, and then there is no LT, it's just that's where you stop there. And so you put in 0.05 and 4, and then I think that's it. I don't think you need, no, you don't need a true there. So it's just like that. So the difference between the two is an RT and then just an inverse, which would be, I guess, the equivalent of an LT, a left-hand tail. All right, now down here, what we've got for number 6 is, let me just change colors here, maybe to a blue. This would be a dist function. So you would put in here then a chi-square dot dist, because dists are always used to find, well, p-values when you're given a particular chi-square value, and then it will tell you the area from some point down. Now, this is from some point down, so you don't need an RT. That would be if you went up. So that's what you'll need here is an RT. But here you put in the chi-square value, which is 4, and then 13, and then you need to put in this true, which is kind of goofy. But so this is your chi-square value. This is your degrees of freedom, and then you always put in a true. All right. When you go up, you'll use an RT there, and then you don't need a true. So it's just kind of goofy that way. So that's the first thing I want to show you. The second thing is just what I find is kind of interesting, and that is where does the symbol chi come from? So the symbol chi actually looks like this. It's like a stylized X. And it's pronounced, it's actually spelled like this, but it's actually pronounced with a long I, so it's chi. So it's not chai, and by the way, that is it might be better to write it this way. So it's a hard CH, so it's chi squared. So yeah, don't ever say chi squared in front of me. Yeah, no. It's a chi-square distribution. The other interesting thing about that, this is the 22nd letter of the Greek alphabet. Phi chi-square, yeah, is the 22nd letter of the Greek alphabet. And it's actually, you've seen this before, actually many times. Here. So I know growing up in a Christian home, sometimes my mother would get upset and say, you know, they're trying to take Christ out of Christmas and replace it with an X. And actually, that's a chi. That's a chi there. And it was actually the symbol that the early Christians used for Christ. So they're not actually taking Christ out of Christmas there. That's where that comes from there, is it's chimus. So that's just a piece of trivia that I wanted to share with you. Anyways, let's get back here then. And we're going to talk about the 5 steps for the classical approach of conducting a hypothesis test. And the thing that you'll notice here is that they're the exact same 5 steps that we used in Unit R when we were testing for means or whether we were testing for proportions. So it's exactly the same thing. And we will find actually that it is the exact same steps that we go through for every hypothesis test that we will do. You always start with your HO and your HA. So your HO is always testing sigma squared, the population variance, or the standard deviation. So you don't have to have sigma squared necessarily. That's kind of standard practice and so on, but I'm fine if you are testing the standard deviation. And it's always equal to some number, you know, it could be 10 or 100 or something, just like we had in Unit R, where we were testing that mu is equal to 120 or something like that. And so that's what we've got here. Just like it would be incorrect for us to put down this, that we're testing that X bar is equal to 10. Remember, we're never testing a sample statistic. We're using the sample statistic to test a population parameter. In the same way, then, we're never testing S squared or S. So that would be incorrect to write it that way. So you're always testing sigma or sigma squared. And then the alternative is that it can be one-sided. So less than K, greater than K, not equal to K. If it's one of the first two, we often change the sign up here at the top to greater than or equal to or less than or equal to, like that. The test statistic, that would be the next thing that we would look at if we were doing a hypothesis test back in Unit R. Remember, back in Unit R, we went through the flow chart. And here, it's actually a little easier because all we're going to do is say, it's always going to come up to this guy here. So your computed chi-square star value will be n minus 1 times s squared over sigma naught squared, where sigma naught is the value in the HO. So it would be K, whatever the K is. All right? So really simple in that way. The rejection region is, well, think if we were doing this with a Z or a T. What we would do is we would look at the sign of the alternative hypothesis, and if it is like that, then it points to the left, and so we would put the whole alpha in the left-hand side. If it's this guy right here, then of course we would put the whole alpha in the right-hand side. If it's this guy here, we would take the alpha and we would split it in half and put alpha over 2 in each tail. So no different from what we have done in the past there. All right, so that is that. And then number 4 is we calculate the chi-square star value based on the sample, just like we would do before, and then we come up with our conclusion. So what we've done here is basically in about 2 minutes gone through how you do a hypothesis test. Let's do it. So we're going to do a class example here. An Army recruitment officer claims, so here you've got the word claims, which means that we're doing a test. And of course you can see the word test down here later, test or claim, that the variance, so you want to find out what is it that you're testing. Is it a mean, is it a proportion, or is it, in this case, a variance or a standard deviation? That the variance in heights of the new recruits is at most 17 inches, well, squared inches, right? Because variances are always in squared measures. So it's 17 squared inches. So the 17 is already a squared number. You don't need to square it. So this then is your sigma squared naught value, the value that's going to appear in your null and alternative hypothesis. To test this assertion, she samples 30, that of course is a little n, and determines that the variation, that's another name for variance, in their heights is 18 squared inches. So that's an s squared. Test her claim with an alpha of 5%. Of course, if you're not given an alpha, you will assume an alpha of 5%. All right, let's go and do it. So, step number 1, your HO and your HA. Remember, always put down the parameter that you're testing. So in this case, it's going to be a sigma squared. And this particular one here, now we're not comparing this to some past claim or some traditional claim or anything like this. When we're given just simply one claim and one number like this, then we assume that that's the standard, that that's the status quo. So that's what appears in the HO. So it says at most 17 squared inches, so that would mean less than or equal to 17. Remember, the 17 is already a squared number, squared inches, against the alternative that it's greater than 17. All right. Test statistic. That's an easy one. It's always going to be this guy. And this, of course, is going to be in your formula book. The rejection region, or more formally, I guess we would say the decision rule. So what we do is we draw a chi-square distribution. By the way, remember that as you're going through these videos, it would be a good idea for you to stop the video and try it yourself, and then pick it up and see if you're getting the same answers as me. All right, what's your degrees of freedom here? Well, your degrees of freedom will be 29, which is n minus 1. And so right off the bat, I like to stick a 29 in the middle here. That tells me that I should be expecting a number either, less than that or greater than that or whatever. And then, let's see, let's take a look at the alternative hypothesis. And that tells us that we're only interested in very high values of chi-square. Remember that the s squared is going to be converted into a chi-square value by this formula here. That's your standardization formula. That would be equivalent to this. Oops, that would be a sigma. That would be the same kind of animal here, but it looks a little different. We're not going to go through the formulation of that, but that's how you change that x bar into a z star. This is how you change the s squared into a chi-square value. All right, so we are going to have the rejection region all in the upper tail because of the sign of the alternative hypothesis here. So we're going to put 5% here, like that. It's not a very good 5. All right, let's go to a chi-square table. 29 degrees of freedom, 5% in the upper tail. And maybe what I should do is just clean this up a little bit here, like that. Okay, so we've got, what was that, 29 degrees of freedom. So here is 29 degrees of freedom. And then we're talking about the upper tail. So that would be the upper 5%. Here's 5% in the upper tail. And so that comes down to, let's see, is it 42.6? That's the guy right there. 42.6 is in the 29 degrees of freedom row. So that's your critical value. Let's go back there. And, need to go a little further here. Okay. So this is 42.6. If you wanted to write that out as a statement, and certainly, of course, it's hard to draw this thing out when you're doing an exam on a computer here, but your decision rule then is that if your chi-square star value is greater than 42.6, then you will reject HO. By the way, since we're here, you know that I really like those chi-square inverse functions and stuff. So this particular 42.6, if you were to find this using Excel, would be a chi-square dot inverse, because you're looking for a critical value, right tail, alpha, and your degrees of freedom. Like that. And that will give you 42.6 as an answer there. So that's your critical value. All right, now we go and we take the sample. And so remember, at this point, really, we haven't seen the results of the 18 yet, but now we do. And so we go in here and we say chi-square star is equal to, what was our n is 30 minus 1 times s squared. Now, this, remember, this is already squared inches, so you don't need to square the 18, but be cognizant of this, that some of the problems are talking about standard deviations, in which case then you would need to square the value. But this is already a squared number, as is this guy here. This is 17 squared inches. And so that comes to 30.71. Now, 30.71 falls in here. And so we would say 30.71 is not greater than 42.6. So therefore, do not reject HO. It's as easy as that. That's how we do that. Why don't we continue on in this video here and take a look at how we would do this with the p-value approach. With the p-value approach, of course, your null and alternative hypothesis will be the same. Your formula is going to be the same. And then what we're going to do here is, well, the calculation of the test statistic here is, I guess really your decision rule is if the p-value is less than alpha, you would reject HO, and then we calculate, and then calculate the p-value. So let's go down here, and what you'll see is it's the same kind of animal as we saw before. So read through this, and let's take a look at what we've got here next. Redo the Army recruiting example using the p-value approach. Do you reach the same conclusion? Sure hope so. So step number 1 is we're going to have HO, and HA is going to be exactly the same. Chi-square star is greater than or less than or equal to, less than or equal to 17 against the alternative that it is greater than 17. Chi-square star is equal to n minus 1 times s squared over sigma naught squared. And then your decision rule is that if the p-value is less than alpha, reject HO. This is your alpha. All right, then we calculate chi-square star is equal to, we take our sample, 30 minus 1 times, what was it, 18, I think, yeah, over 17, and we get 30.71. And that's where we now go to a chi-square table. So let's take a look at a chi-square table. Here's the distribution. 29 degrees of freedom. always put the 29 in here just to make sure that it the number that you get when you do the calculation makes sense. In this case, that we are talking about an upper tail value. We're talking about calculating from 30.71 up, and that will be the p-value. Now, if this were a two-sided test, we would find the area and we would double it, just like we did back in Unit R. Okay. Remember, though, that you take a look at the sign of the alternative hypothesis, and so even if you ended up with a really low chi-square value, maybe down here, you know, this was, let's say you ended up with a chi-square value of 20 or something like that, you would still calculate the p-value going up. So you'd end up with a very high p-value, and you would just compare that to alpha. So it doesn't matter which tail you're in, with the exception of a two-tail test, then you take a look at the tail that you're in. But with a one-sided test, you always look at the sign of the alternative hypothesis, and that is like an arrow that points either up or down. And so you could end up with a very high p-value. And that's okay. Now I'm going to just get rid of that there. And we're going to get back to where we were, so 30.71. So what we do is we go over to our chi-square table, and we're going to go to 29 degrees of freedom, and we're going to find out where does 30.71 fall. And in this particular case, then, we're going to find that it's, let me just get rid of this guy here. This was our critical value for 5%. But in our case, then, we end up with 30.71 is right in here. Okay, I'll put that at the bottom here. I don't really have room there. So 30.71 is there. So it's between, it's in that middle range. 19.8 is 10% to the left, but 39.1 is 10% to the right. So let's take a look at what we've got here. I'm going to put in both of those numbers here just to show you, again, how we read the table here. 19.8 and 39.1. So what this is showing us here, I'll do this in a different color, is here's the 19.8. That would be 10% to the left-hand side. And then we've got, I guess it would be over here. We've got 39.1 corresponds to 10% in the right-hand tail. I know those aren't drawn proportionately here. But we're not really interested in this part here. We're only interested in the area going up. So what we would say here then is that the p-value is greater than 10%. Okay, so the p-value is greater than 10%, and therefore do not reject HO. Last thing here is what would be the chi-square value that would give me this 10% here, and it would be a chi-square dot dist, because it's a p-value, right tail 30.7129. So this is your chi-square star. This is your degrees of freedom. Notice that it's right tail, and it's a dist function for a chi-square distribution. And that will give you, it'll give you a number actually more exact than a 10%, but it will be something greater than 10%. All right, that is where we're at. The last part that we'll look at here in the next video will be how to do a confidence interval for chi-square, and then for homework we'll run through a problem here. Okay, let's end the video here. Thanks for listening.